Now we're going to focus on the atmospheric circulation system. Because the Earth is not a flat disk perpendicular to the Sun, it behaves in a far more complex way. This diagram summarizes many of the features of the atmosphere that are important for this portion of the course. Hopefully by the end of this series we'll gain an understanding of what this figure means in all its complexity, and once we get to that point we're going to have a pretty good understanding of how this whole system works, starting with the Sun, ultimately feeding back to our daily experience in terms of climate and weather. When we talk about the atmospheric circulation, we have a couple key questions we're going to address. Number one, why does the air move? Number two, are the movements of the winds, the air, random across the surface of the Earth, or do they follow regular patterns? What implications do these circulatory systems have for global climate? What other factors govern the geographic and seasonal distribution of temperature and precipitation? It would be a whole lot easier for us to envision how things work if there's some pattern, some regularity, some consistency with the manner in which the atmosphere circulates. And as we'll see, there are. We'll start with the website, windy.com. It offers a bunch of cool ways to look at the current meteorological situation all over the Earth. We'll take a look at how that works here. When you open the web page, windy.com, you're going to see a screen like this. It's going to focus on your geographic location, so wherever you're logging in, that's going to be the center of the image, presumably. There are a number of menu items over here to the right that we can use to see different aspects of the current meteorological situation on Earth. We'll start out at the top here with radar and satellite. The weather radar looks pretty quiet. Oh, here it is. This is the current meteorological situation in terms of radar imagery, which is, in this case, going to be bouncing radar waves off of falling precipitation and moisture in the clouds. When we look at a satellite image, we can see the clouds in visible wavelengths of light. This is what you would see if you were currently orbiting the Earth in the space shuttle, for example. When we look at winds, we can see the airflow in the atmosphere. These little arrows, the streams that they depict, are the flow of wind at or near the Earth's surface. Now, if we zoom out away from Saskatoon, you'll see there's a lot of things going on in the world at any given time. Now, out here in the Pacific, we could see what's probably the beginning of a storm centered here just north of the western Aleutian Islands. If we look here, down in the area of Southeast Asia, Indonesia, we can see a very well-developed storm system. Now, this would be equivalent to hurricanes that we see in the Atlantic Ocean. In the Pacific and the Indian Ocean, we call them typhoons and cyclones, but they're the same as a hurricane. Backing off and traveling south, we can see there's a whole lot more action off the coast of Antarctica. This is the Antarctic coast here. And let's see, the Antarctic Peninsula is located over here. This is the shortest transect between a large continent and the Antarctic continent here, known as the Drake's Passage, or the Drake Passage. And it's going to be a location of very extreme winds and waves, as we'll see. Returning to North America, we can see Saskatoon located just to the center upper portion of the screen here. Not much happening in Saskatoon on this date, Saturday, August 29th. But down here to the south in southeasternmost Colorado and northernmost New Mexico, we see a storm cell developing. You can hit play over here to the lower left and run this storm model forward. So you can see this storm developing. It's increasing in intensity. Now it's decreasing in intensity. It's establishing itself, increasing intensity again as it moves to the east. We can see a wave moving across Canada as well. We'll just move this back a little bit. So we go from the current situation, Saturday afternoon again, running this forward, we're going to see the development of a storm system here. Coming out of Alberta, and it's transecting east and south across Canada and the northern tier of the US. Ultimately, it's either going to dissipate or make it to the Atlantic Ocean, where it may strengthen depending on water temperature. And it looks like it's probably going to strengthen, as you can see developing up here. Now we can look at rain accumulation, a different map here. We can look at that for the next 12 hours. Looks like it's going to be clear and dry. 24 hours, also clear and dry. Next 5 days, looks like it's going to get cloudy to the north. But we're going to stay pretty clear of precipitation here in Saskatoon. Down in the US, it's a different story, where humidity is much greater, and the contrast between the hot, wet air of the Gulf and the dry air coming off of the Rockies is going to lead to this severe storm situation that often develops along this belt, which is known as Tornado Alley in the United States. Okay, what else can we do? We can click on temperature over here and look at a current temperature map. Actually, this is for Tuesday. It hasn't happened yet, technically. And again, you can hit play and run this temperature profile forward for the US and southern Canada. And you can see heat waves develop and then move across the continent. Now, cloud cover, we can look at that in a couple different ways. We can look at low clouds. We can look at the cloud base. Seen here, again, transecting North America. We can look at visibility. This would be most important to people flying small aircraft. And occasionally if you're driving a car. Waves, not particularly important for us here in Saskatoon, but if you are out on the Great Lakes, Lake Superior is known for its storms, it's known for its waves, and that's in part due to its very large size. You can see there's some considerable wave action here. Now, backing off a bit to get a global perspective of this, where you see these colors, these very vibrant purplish colors, those are very high waves. When they get lighter again in the center of these purpley areas, the waves are on the order of 10 meters or more. So those are pretty energetic waves. And you'll see they're a lot more common down here in the Southern Ocean. A very exciting place to travel by boat, I can tell you. So we're seeing waves that are typically on the order of 10 meters here, 30 foot or more in several locations. This is not uncommon. Remember, it's springtime coming up soon in the Southern Hemisphere. So these are the spring storms in the Southern Ocean. We'll take a look at sea temperature here. And along with the sea temperature, you'll see some flow lines here that represent the motion of the surface currents, where we have this reddish color, temperatures are relatively high, where we have the greens and blues, temperatures are relatively low. Commonly off the coast of the Antarctic Peninsula here, water temperatures are around -1.5 or so. Below freezing of fresh water, but not below freezing of seawater. There's an interesting thing that happens when seawater does freeze, when it gets colder than that we'll talk about a little later in the course. Now, air quality. This is kind of interesting. We can click on aerosols. That's not going to be particularly interesting. Here, PM 2.5. This is particulate matter, with a diameter of less than 2.5 microns. Now when we click on that, you'll notice some areas that are relatively clear all over the high latitudes of North America, relatively clear. But down here in southeastern British Columbia, southwestern Alberta, we see some particulate matter. Out here near Victoria, particulate matter. Oregon and down through California, again, we see a lot of particulate matter. Now this can be dust from an arid region. In this case, it's not dust. We're going to zoom in a little bit. We can see this patch of considerable particulate matter here, centered right at the coast of California. What is this? Why is California so dusty? Well, it turns out there are fires all over California right now. 375 to 400 or so. The numbers are kind of all over the place right now because these fires are breaking out, being fought on a continuous basis. This is a long-term drought situation in California that's spawning these fires to a large degree, coupled with the seasonal winds making it worse. So if we move out away from California a bit and then start the animation here, do a little time travel, you can see the smoke appearing from these fires and then transecting east. Now, the smoke was affecting the visibility and air quality of the easternmost United States yesterday, to be August 28th. There's a clear spot down here, you may notice, in the southern U.S. This clear spot was generated by Hurricane Laura, which we'll take a look at in a few minutes. So that hurricane came out of the Gulf and pretty much moved along this track. And wherever that hurricane moved, the precipitation cleared the sky of this particulate matter. But you can see this is going to be an ongoing problem. I don't know how long. I'm guessing probably several weeks, maybe more. Australia suffered some very severe fires in January of 2020, December of 2019, back into November and October of 2019. They killed an estimated 1.5 billion animals. So really tragic situation there that also generated huge plumes of this particulate matter. I'll leave this to you guys to play around with. It's really cool if you're a geek. If you're just into swirly colors, it's also kind of cool. Fortunately for the people in the southern U.S., this hurricane quickly dissipated once it reached land. When a hurricane does reach land, apart from generating a lot of damage, it is removed from its power, from its heat source, which in this case would be the Gulf of Mexico. And by taking that power away, the strength of the storm is diminished. As it moves across the United States, you'll see it get weaker and weaker. This is the storm that squeegeed all of the dust from the California wildfires from the sky of the southeastern United States. Once it reaches the Atlantic here, it hits the Gulf Stream and can re-intensify. And we'll see what's in store for our future tomorrow, the 30th of August. Now that we've seen some examples of current circulation in the atmosphere from windy.com, we can start to take a look at the global circulatory subsystems of the Earth. Now we need to do this to gain an understanding of these components and how they act on their own and relative to each other. Many of these components of the Earth are in motion. Some of the more easily visualized examples are the atmosphere. We can see and feel the wind, for instance. The oceans, we can feel ocean currents. We can see and feel waves. And biological systems. We see trees and flowers bloom in the spring, grow during the summer, lose their leaves in the fall, go dormant for the winter. There's a movement of animals in and out of ecosystems. Birds are the best example. They migrate long distances, sometimes 14,000 kilometers or more. And we have some components that move very slowly. The continents are always moving, but very slowly. The mantle is in constant motion, has been in motion since it developed roughly 4.5 billion years ago. Now, the mantle didn't really develop then, but shortly after. Each of these systems play a role in the distribution of energy and therefore the climate of the Earth. These systems can be thought of as acting on 4 different time scales. Number 1, very short time scales. These are things we would experience, things that last for days to weeks. And a good example is surface winds. If you think about surface winds, the most dramatic examples are those associated with storms. We can talk about short time scales. These are time scales of years to decades. And a good example of that is the movement of ocean heat from the east to the west and the west to the east in the Pacific at the surface is going to affect what's going on below the surface. And a good example of that is El Nino La Nina, or ENSO. Longer time scales are millennial in length. A good example of this is deep ocean circulation. And an example of deep ocean circulation comes from the Gulf Stream, which is a surface current. This surface current is going to be very important in generating deep water. And in doing so, it's going to be very important in generating deep water ocean circulation. And lastly, we have the longest time scales, tens of millions of years. The examples that, again, we can see a record of, we don't see it necessarily happening except in extreme events like earthquakes, but we can envision it by using geological reconstructions. An example of this would be plate tectonics, the movement of the continents relative to one another, and the building of the Himalayas. Starting with number 1, very short time scales. Again, think of storms and weather frontal systems. Here we have an example of short-term climate. This is the development of a hurricane. Once winds reach a speed of 74 miles an hour, the storm is known as a hurricane. Now, this hurricane season begins at the beginning of June, ends at the end of November. That's when most hurricanes take place. Now, just recently, Hurricane Laura hit the southern coast of the United States with wind gusts of 185 miles an hour. That's a Category 4 hurricane, almost a Category 5 hurricane.